You know, one of the wildest ideas in all of physics is that time isn't fixed. It can actually slow down. For over 100 years, we thought we had the perfect explanation from Einstein. But what if he was wrong? Today, some bold new theories are challenging everything we thought we knew. So in this explainer, we're going to break it all down, the established idea and the radical new ones trying to take its place. Let's get into it.
So we've all heard it, right? Gravity slows down time. It's a fact of our universe, proven by everything from the GPS in your phone to super precise atomic clocks. But have you ever stopped to ask why? I mean, what is physically happening that makes a clock tick slower just because it's closer to, say, the Earth? That question? Well, that's where the real fireworks start. And it's where a century of physics is now being challenged.
Okay, so before we get to the challengers, we have to understand the reigning champion. We need to start with the idea that has been the absolute bedrock of physics for more than a century, Einstein's theory of general relativity.
And here's the absolute genius of it. Einstein basically threw out the old idea of gravity as some mysterious, invisible force pulling on things. Instead, he said that huge objects, like planets and stars, literally bend and warp the fabric of reality itself, what he called spacetime. You've seen the classic example, right? A bowling ball on a trampoline? The fabric sinks down and curves. That curve? That's gravity. So in Einstein's world, everything, you, me, light, and even time itself, has to follow these curves in space-time. When you're in a strong gravitational field, like near a planet, that curve is much deeper. So for time, moving through that deeper divot just takes longer, compared to somewhere with flat space-time. It's this beautiful geometric explanation, but it does leave one huge question just hanging there. What's actually causing the warp?
And that question is exactly where our first challenger comes into the ring. See, Vladimir Leonov is looking at this from the weird world of quantum physics, and he's proposing something totally different. Forget geometry, he says. It's all about particles.
And just listen to this quote, because it pulls no punches. He's not just trying to add a little something to Einstein's theory, he's saying the whole foundation is wrong. He's arguing that time slowing down is a pure quantum effect, and we don't even need relativity to explain it.
So what's his big idea? Get ready for this. Leonov's theory introduces a new hypothetical particle. He calls it the 4D tetraquark. And you can think of these things as the universe's tiniest, most fundamental little clocks. His idea is that space-time is literally packed with these things, and each one is constantly ticking away, defining the very flow of time itself.
So, here is the absolute game changer. In Leonov's model, time doesn't slow down because of a curve in spacetime. No, it slows down because gravity, as a real force, is physically pushing on these little time particles and slowing down their ticking rate. The stronger the gravity, the slower they tick. And if they tick slower, well, time itself passes more slowly.
And this isn't just some vague idea, you know? Leonov's theory actually makes a specific, testable prediction. He calculates that right here on the surface of the Earth, our planet's gravity is slowing down those fundamental quantum ticks by about 1 second every 100 years, compared to a clock way out in deep space. Now that sounds tiny, but in physics, a number you can test, that's a huge deal.
All right, you ready for challenger number 2? Edward Wu also thinks particles are the answer, but instead of focusing on particles of time, he's focused on the particles that he believes cause gravity.
Wu's idea paints a totally different picture of gravity. Forget the smooth, silent trampoline. Instead, imagine gravity as a constant physical storm. In his model, every massive object is constantly shooting out a dense stream of particles called gravitons. So gravity isn't a warp in space, it's the literal pressure from this constant bombardment of particles.
And how this works is actually super intuitive. Just imagine you're trying to operate a delicate little watch inside a sandstorm. All those grains of sand would get in the gears and physically slow it down, right? Wu says that's exactly what's happening with gravitons. This constant storm of particles literally interferes with the inner workings of any clock, whether it's mechanical or atomic, and slows it down. The bigger the planet, the more intense the storm, and the slower the clock runs.
Okay, so let's just boil this down, because this is the key difference. For Einstein, what slows down time is your speed or acceleration as you move through that curved spacetime. But for Wu, nope. Speed has nothing to do with it. All that matters is how strong the local gravitational field is. Basically, how intense the graviton storm is right where you're standing.
And all of this builds up to the biggest showdown of them all, a disagreement that goes right to the very core of how we think the universe works.
We're not talking about a small disagreement here.
This is a battle for the soul of physics. These theories are locked in a fight over the one number we all thought we could count on to be absolute, the speed of light.
This table just lays it all out so perfectly. Einstein's entire universe is built on the rock-solid idea that the speed of light in a vacuum is always the same. It is the ultimate speed limit. But for Leonov's theory to work, and for Wu's theory to work, the speed of light can't be constant. They both predict that gravity doesn't just slow down time, it physically slows down light too, and you just can't have it both ways. This is a fundamental head-to-head clash.
So, we've looked at warp geometry, we've looked at quantum ticks, we've looked at graviton storms. After all of that, what are we supposed to think? What's the real story here about the nature of time?
You know, the big takeaway here isn't about picking a winner. It's about seeing how science actually works. For 100 years, Einstein's beautiful geometric picture has been king, but there's this one nagging problem. We still don't know how to connect gravity with the quantum world. And that mystery is what's forcing physicists to ask these huge, radical questions. These new theories, whether they end up being right or wrong, are part of that incredible push into the unknown, where you have to be willing to question everything, even the speed of light.
And that leaves us with one last kind of mind-bending thought. If these challengers are right, if time isn't some fundamental fourth dimension we're all traveling through, but is instead just an effect of tiny particles ticking and bumping into each other, a giant clockwork machine on a cosmic scale, what does that do to our whole idea of reality? It's a question that proves the search for how the universe really works is nowhere near finished.